and get started. So back in the days of Edison and Tesla, there was a lot of discussion and argument about whether DC current or AC current was the way to go. And Edison fought for DC current and Tesla fought for AC current, and AC current won because you just can't transport DC current over long distances. And so in order to get power out, AC is the way that makes sense. And so alternating current means that you've got a sinusoid. And so that means that our voltage, when we're looking at AC currents, is, well, that's what the A stands for, is alternating. And so voltage and current are sinusoidal in AC circuits. So unlike everything that you did in circuits 1, where you would have direct current where you would just have a number, now we've got a function, and it's a sine function. And sine functions can be really difficult to deal with. And so you can do all of electricity and magnetism using sines and cosines and without ever involving imaginary numbers, but it is a real hassle. And what helps out a lot is Euler's formula, relation, Euler's formula, I'll say formula, that E to the j theta equals cosine theta plus j sine theta, where j is the square root of -1. And in physics and math, they use I, and engineers use j, which makes sense because we use I for current. And exponentials are a whole lot easier to deal with than sines and cosines. And so what we do is, rather than deal with sines and cosines, is we deal with these exponential functions. Because when you deal with exponential functions, if I multiply e j theta 1 times e j theta 2, when you multiply, you just add exponents. That becomes e j theta 1 plus theta 2. So that makes it really easy to deal with. And so rather than having to deal with these sines and cosines, we just use exponentials. And we use even more of a shortcut than that, in that it's really the frequency is not as important as much as the phase shift. So if you're looking at a cosine or a sine, for instance, so here's sine. If I have everything in my circuit is operating at the same frequency, then they all look kind of like this. They all have the same, well, they might have different amplitudes, but if they all have the same frequency, what's really important is their phase shift, how far apart they are from each other. And so phasors use just the magnitude, which would be the same as the amplitude if we're talking about the sine or cosine graph. The amplitude and phase shift, so how far apart the voltage and the current are from each other in terms of phase. And so if I'm looking at something like a voltage V of t equals 10 cosine 60t plus 45 degrees. First of all, it's always been kind of weird to me that this is how it's done in electrical engineering, but this is in radians, but this is in degrees. And this is the phase shift. And the number in front of the t is called the angular frequency. And the angular frequency is the Greek letter lowercase omega. So that's an omega, and it's lowercase. It's a lowercase omega. So that's the angular frequency. And it's related, and that's an angular frequency is in radians per second. And it's related to a regular frequency because an angular frequency is talking about like a whole cycle. So a regular frequency would be in cycles per second, or usually we just deal with the per second part, which is a hertz. So it's the number of cycles per second. But an angular frequency is radians per second, and we know that there are 2 pi radians in a cycle. So angular frequency is equal to 2 pi f. So if something is 60 hertz, which is what we see in AC circuits around here, so if frequency is 60 hertz, its angular frequency is 2 pi times 60, which is like 324, 2 pi times 60, 377 radians per second. Okay, so what we do is we take our voltage here, which was as a cosine, V of t equals 10 cosine 60t plus 45. And we write it as a phasor, and we just write 10 angle 45 degrees. And so what that doesn't capture is the frequency, but it captures everything else. So this is the magnitude, or it's also the peak voltage. And this is the phase shift relative to something else. And so when we write phasors, by convention, I'm sure the book y'all are using does this too, we use cosines instead of sines. So by convention, phasors use cosine. And also, you'll notice that if I go all the way around the circle and then go all the way around the circle again, I'm repeating values over and over again. And so by convention, we put the angle is between negative 180 degrees and 180 degrees. So like if I had a phasor that was 5 angle 200 degrees, I would just rewrite that as 5 angle negative 160 degrees. You're subtracting it from 360 degrees. And the other thing to note is that sine omega t plus theta equals cosine omega t plus theta minus 90 degrees. So if it's given to you as a sine, we can turn it to a cosine by subtracting 90 degrees. So if I have 13 sine omega, or I could have any number there I wanted. 5t plus 40 degrees. I would want to have that as a cosine because I'm going to have all my phasors in terms of cosine. That'd be 13 cosine 5t plus 40 degrees minus 90 degrees, which would be 13 cosine 5t minus 50 degrees, which is 13 angle negative 50 degrees. Another thing that we want is, since we're talking about cosines and we're talking about our amplitude being the maximum height, we don't want to have a negative number in our phasor. So if I had something like negative cosine 60t plus 45 degrees, the way to, well, it's negative 5. The way to turn that into a phasor is I have to get rid of the negative, and to get rid of the negative, so if I look at a cosine graph, so this is v equals cosine t, and this is 180 degrees. And then if I look at a negative cosine graph, so this is v equals negative cosine t. Or if I look at this cosine graph and I shift it by 180 degrees, so this is cosine shifted right by 180 degrees, I see that these two things look the same. And so the way I can turn a negative cosine into a positive cosine is to shift it by 180 degrees. So I would have 5 cosine t plus 45 degrees minus 180 degrees, or 5 cosine 60t minus 135 degrees, or 5 angle negative 135 degrees. So that's my introduction to phasors. So now let's take a look at, I'll come back to these definitions, and let's transform. Let's look at problem number 1. Let's transform these into phasors. And the reason we want to do this is because we want to work with everything with phasors rather than with using sines and cosines. So, do you want to tell me how to start with the first one? Yep. Do I want to use sine? Okay, so we want to use cosine. And so we want to change it to cosine. And the way we change sine to cosine is by subtracting 90 degrees. So we would write this as 10 angle negative 15 degrees. Okay. Now, with my second one, do you see any difficulty with the second one? Yeah, and we don't want a negative magnitude. So to make it a positive magnitude, I said subtract 180, but you can either add or subtract 180 because either way is going to make it the same as being negative. And remember that we want to keep this number between positive and negative 180. And so in this instance, it'd be easier to add 180 degrees. And I'll show you what we would do if we subtracted and just how we would adjust it. And so that's plus 155 degrees, I think. 17 angle 155 degrees. Now, you could have subtracted it. So we could have done 17 cosine 9t minus 25 minus 180 degrees. And that would get us 17 cosine minus 205 degrees. But now that's not between negative 180 and positive 180. And so you would add or subtract 360 to get the equivalent angle. And if I add 360 to negative 205, I get 155, so I get the same thing. I just had one extra step to get there. You took Digital Logic 2 last semester? Or? Oh, okay. And that's everything you need to know about circuits too. Oh, yes. So what I did, and you can watch the video later because I am recording even though you weren't here to remind me, is I went over a little bit about phasors and why we use them, and how to form them. And so it's yet another way of writing complex numbers, but specifically dealing with sine and cosine functions. And what the quick summary so far is as follows. So if I have something that looks like m cosine omega t plus theta degrees, then this is my magnitude or my altitude or my peak value if I'm talking about a voltage or a current, and I want it to be positive. By convention, we use cosines instead of sines. The number in front of the t is the Greek letter lowercase omega, and it is the angular frequency. And the angular frequency is in radians per second, and it's related to the frequency by the omega is 2 pi f, where f is in hertz or per seconds. So the frequency is cycles per second, and omega is radians per second. And notice this is in radians, but this is in degrees, and this is the phase shift, are often just called the phase. And so it's how far it is shifted. So you'll have, usually with most of the circuits you'll be dealing with, everything will have the same frequency. They'll all have the same omega, but they might have different phases, and that's going to affect how they interact. And when we write this as a phasor, so that we don't have to deal with the complexity of sine and cosines, we write it as m angle theta degrees, and by convention we have theta between positive and negative 180 degrees, and if it's not, you just add or subtract 360 to get it there. So add, subtract 360 degrees if necessary to get it there. And then we went over a few things to do if it's not already given to you in that nice format. So, if it's already given to you, like 6 cosine 16t plus 32 degrees, well, that's easy. That phasor is 6 angle 32 degrees. Notice we lose information about the frequency when we turn it into a phasor. If I had 8 cosine omega t plus 190 degrees, that's not between plus or minus 180. So I would subtract 360 from it, and I get 8 cosine omega t minus 170 degrees, and that would be 8 angle negative 170 degrees. What's that?
Subtract 360.
Yeah. So I'd subtract 360 because subtracting 360 gets me between plus or minus 180. Did the table just buckle? It does that. It's just, it likes to do that for fun. I don't know what to do about it. I just don't sit at that one. Yeah. So if we have sine, we have the identity that sine omega t plus theta equals cosine omega t plus theta minus 90 degrees. So if you're given a sine, you turn it into a cosine by subtracting 90 degrees. And so the first example we did was a sine. We had 10 sine 8t plus 75 degrees. We subtracted 90 from it to get 10 cosine 8t minus 15 degrees, and that'd be 10 angle negative 15 degrees. And then the next thing that you can do, you always want your amplitude to be positive. So if I had negative m cosine omega t plus theta equals m cosine omega t plus theta plus or minus 180 degrees. So if I need to turn it to a positive, I can either add or subtract 180 degrees, and that'll make it positive. So the second example that we did, that I was almost done with when you walked in, no, I was done with, yeah, was negative 17 cosine 9t minus 25. I didn't want a negative in there, and so I added 180 degrees, and I did that because adding 180 degrees got me between negative 180 and positive 180. I could have subtracted 180 degrees, but then I would have been smaller than negative 180, so then I'd add 360 and I'd still get 17 cosine angle 155 degrees. Okay, now the last one we're going to do is going to be harder. Oh, I'm not going to re-review. So you'll have to watch the video because I did it once and then I reviewed it, and so yeah. Okay, so the next one, I3 of t equals 8 cosine 6t minus 45 minus 5 sine 6t. Now, phasors, it's very easy to multiply and divide phasors. It's a lot harder to add and subtract them. You usually have to turn them into, or I have to turn them into A plus BJ format to do that. So, first what we'll do is we'll write this first one as a phasor would be 8 angle negative 45 degrees. Then we need to change the sine to a cosine, so it'd be cosine 6t minus 90 degrees. So then this is 8 angle negative 45 degrees minus 5 angle negative 90 degrees. Now, if you have gotten the calculator that I recommended and have been recommending for a couple years, all of these calculations become very easy because it just does it. But I'm going to show you how to do them, and then I'll show you how to use that calculator. Hold on a second. I'm pausing. Okay, so let me get the calculator. TI Smart View. Okay, now just getting that started. Okay, so what we need to do to add them is we can't add them just as phasors. So we turn them in, we use Euler's formula. We turn this into 8 sine negative 45 degrees plus j cosine negative 45 degrees minus 8j minus 5. I did that backwards, sorry. It's cosine minus sine. Eight cosine negative 45 degrees plus j sine negative 45 degrees minus 5 cosine negative 90 degrees plus j sine negative 90 degrees. So this gets us 8 times square root of 2 over 2, which is 0.707. 0.707 minus j 0.707 minus 5 cosine negative 90 is 0, and the sine of negative 90 is minus 1, so minus j. So this is 5.657 minus j 5.657 plus 5j which is 5.657 minus j 0.657. Now, when you have something in a plus bj form, the magnitude is the square root of a squared plus b squared. So it's the square root of 5.67 squared, 5.657 squared plus negative 0.657 squared What's that? Yeah. Yeah, that's, which is 5.69. And our angle is the inverse tangent of b over a if in quadrant 1 or 4, and it's the inverse tangent of b over a plus 180 degrees if in quadrant, and I'm putting this because the calculator will only give you the quadrant 1 or 4 value, if in quadrant 2 or 3. And so this particular number, so this is our real axis, this is our imaginary axis, and so the real axis, it goes out 5 and down about 0.6. That's quadrant 4. That means if I take on my calculator the inverse tangent of minus 0.657 over 5.657, the answer I get will be correct. So the inverse tangent of negative 0.657 divided by 5.657 is negative 6.62 degrees. So all of that tells me that my answer is 5.69 angle negative 6.62 degrees. Now, on this calculator, is this the right one?
This is 30x.
Yeah, it's the same as the 36x though. Okay, so a couple things you want to check on it. First, mode, you want to make sure you have it in either a plus bi form or r angle theta. You really want to get one of these. If you don't have one of these, they're only like $20, and you'll see in a minute.
The 36x Pro.
36x Pro from Amazon. You also will want to make sure you're in degrees. So degrees. Okay, so then like the one we just did, we had once we got it into phasor form, it was 8 angle negative 45 minus 5 angle negative 90. And this online one doesn't, it gives it to me exact. It doesn't, the regular calculator like tells me what that actually is. So 5.65 minus 0.656, so minus j 6.656. So that's there it is in a plus bj form, or I can go to the complex menu and say turn it into polar form, and it gets me 5.69 angle negative 6.62 degrees. So, and it can do all of the arithmetic. So anything that y'all have done in class with complex numbers, it'll do just fine. So like if I have 2 plus 6j over 3 minus 2j plus 6j, and then if for fun I want to combine formats, 9 angle 32 degrees. There it is in a plus bi form, or I can go to my complex menu and get it in polar form, and there it is. And I can also get in the complex menu, I can get just the angle, or I can get just the magnitude, and I can get its conjugate, I can get the real part, I can get the imaginary part. So it does it all. And even that bit about worrying about which quadrant it's in, it takes care of that too.
I didn't realize you could do all that.
And yeah, it does all that. So, okay, so let's take a look at an example. First of all, you use differential equations to show that if we change everything to phasor form, so if you want a handout, I have one here.
This,
Yeah. Since you're standing,
sure.
would you go get the stuff off my printer? It has the I have the solutions, but it has them printed out so I can check them. Thank you. Okay, so you may remember from circuits 1 that when you start dealing with inductors and capacitors, that you start dealing with derivatives and you have differential equations. So another reason that we use phasors is it takes our circuit from a differential equation that has sines and cosines in it into an algebraic equation. It has complex numbers, but it's still just an algebraic equation, not a differential equation. And so the equivalences are that the resistance remains the resistance. So resistance is real and resistance is always R. L in the phasor domain becomes J omega L, where omega is the angular frequency and L is the inductance. And C, here it's 1 over J omega C, but I usually use, instead of 1 over J omega C, I do negative J over omega C. And so if you have 1 over J omega C, if you multiply that by J over J, then you get J over J squared omega C. J squared by definition is -1, so J over negative omega C, or minus J over omega C. So usually for the capacitance, we'll do minus J over omega C. And that also lets you see that is negative, whereas the inductance is positive, imaginary, negative imaginary, and positive imaginary. And then once you do this, you can treat inductors and capacitors just like resistors. So you can add them in parallel and in series and all of that. And this little chart shows you that if you are in DC, or very low frequency, an inductor acts like a short circuit and a capacitor acts like an open circuit. But if you're at very high frequency, if your omega is very big, it's the opposite. An inductor acts like an open circuit and a capacitor acts like a short circuit. And we have this term, Z, impedance. And impedance is like resistance. Impedance is the ratio, it has a symbol Z, and it's the ratio of V over I as phasors. So just like in time domain, V equals IR, in the phasor domain, V equals IZ. And Z is just the combination of all of your elements. So if we look at these things here, so impedance, So impedance, I just defined that for you. That is Z over I. Resistance, this is the real part of impedance. So impedance will be, it'll be the form A plus JB. So I'll have a real part and an imaginary part. The reactance is the imaginary part of impedance.
Impedance is Z over I?
No, sorry. V over I. It has the symbol Z. So the reactance is the imaginary part of impedance. And when we say imaginary part, you don't put the J with it. So when I say imaginary part, it's the part without the J. So inductive impedance, so that would be the impedance of an inductor.
Question.
Yep.
You said the reactance is the imaginary part. You said that's with or without the J?
Yeah, I explained that. So let me get the. Okay, so it's a weird thing that when it's just it's terminology. So if I have 6 plus JB, or 6 plus J, four. The real part of 6 plus J4 is 6, and the imaginary part of 6 plus J4 is 4. I just don't write the J. And so it's weird that it's the imaginary part, but we don't put the J on it.
Oh, okay.
Okay, so it's like it's hard to answer that. Does it have the J or not? Well, yeah, but we just yeah.
Okay, I get it.
So I would say the resistance is 6 ohms, and the reactance is 4 ohms. And reactance has the symbol X. I didn't put that in there, so reactance is X. And resistance is R. And so impedance Z equals R plus JX. So the inductive impedance is J omega L, which is greater than 0. And the capacitive impedance is minus J over omega C, which is less than 0. Admittance, you're not going to use that much, but in the future you'll have some professors that like conductance instead of conductance instead of reactance, and there'll be some that like admittance instead of impedance. So Y is just 1 over Z.
So it's just the inverse.
Yes. And conductance, it has admittance just like impedance has units ohms, just like reactance. Admittance has in units Siemens. Conductance is the real part. It's G, it's the real part of the admittance. And the susceptance, B, is the imaginary part of the admittance. You're probably not going to see these. Just the last instructor had a question on the first test where you had to find the conductance, and it was like, it would have been real easy if people remembered what conductance was, but it's just not remembering what it is. Let's see. Okay. Okay, so now let's take a look at this problem. So what we're going to do is we're going to transform everything into the phasor domain. The first thing I notice, because I will forget it if I don't notice it, is that this is in milliamps. So this is 0.0, that's the, I'm changing my phone number. By the way, I'm changing my phone number.
Okay.
0.012 cosine 2 pi times 10 to the 4th t minus 60 degrees. Okay, so 0.012 is my magnitude. Omega is 2 pi times 10 to the 4th. And I have to kind of write that out to the side because that's not going to be part of my phasor. My phasor is going to be I equals 0.012 angle negative 60 degrees, and I have an angular frequency of 62,831. Okay, so that's I. My resistors are the best because they never change. It's just 20 ohms. My capacitance is going to be minus J over omega C. So that'll be minus J over 62,831 times 1 times 10 to the minus 6. And I'm going to say minus, and the J on this calculator, there's a button that has pi EI. You just have to press it 3 times to get to the I, which is a J. And then it was, don't remember what it was, but it was 2 pi times 10 to the 4th. And the capacitance was 1 microfarad, so 1 times 10 to the negative second. So minus 15.9 I, or minus J 15.9. I don't know why they like to put the J in front, but they do. Okay, so now in phasor domain, and I want to get I through the capacitor. So I can use current division. So if you remember from circuits 1, current division. So if I have a current, I have R1 and R2. If I want I1, and so I1 goes through the first resistor and I2 goes through the second resistor. I1 equals I times R2 over R1 plus R2. That's the 5th phone call since I've been sitting here, not counting my sister. It's I times R1 over R1 plus R2. So that was current division in DC. Current division in AC will be I1 equals I times Z2 over Z1 plus Z2, and I2 equals I times Z1 over Z1 plus Z2. So if I want the current through the capacitor, so IC will equal 0.012 angle 60 degrees times minus J 15.9 over 20 minus J 15.9. And here is where I'm really glad that my calculator will do mixed computations. So I will do open parentheses 0.012. Now go to my complex menu, angle 60. Was it 60 or negative 60? It was negative 60. Times, and then I use my fraction to keep everything so I don't have to deal with parentheses, minus J 15.9 over 20 minus J 15.9, and I get an answer of negative 0.0027. And then you always have to arrow over to see the imaginary part. Minus 0.0069 J. Or as a phasor, so to turn it to a phasor, once I've had that, I go, or to polar form, I just go to second complex and change it to R theta, and I get .0075 angle -11. No, angle -111. That's not what I got. Where did I go wrong? I wanted the current through the capacitor. I wanted the current through I wanted the current through the capacitor, so this should have been Z1. That should have been 20.
Current division doesn't look familiar to me.
I know it wasn't covered enough, but it's very handy.
I also like that fraction button.
Yeah, the fraction button is great. Yeah, that's right. Okay, so it was 0.008 7 minus 0.034J or as a phasor 0.0094 angle 21.5 degrees. But the problem actually asked us to get lowercase ic of t, so we need to turn this back into the time domain. So 0.0094 is 9.4 milliamps cosine, and you'll have the same angular frequency, which was 2 pi times 10 to the 4th t. And then plus 21.5 degrees milliamps.
So whenever we switch back the omega t part
It's the same.
It's just
Yep.
like, hey, welcome back.
Yep, welcome back. We ignored you for all the calculations. Yeah, so just real quick with current division, whenever you have a current and it breaks up into two parts, you get the individual current is the total current, so you get the current division is the current in one branch equals the total current times the impedance or resistance of the other branch times the sum of the impedances. And I find it easier to do than finding the voltage and then finding the current from that, but you could do it that way too. All right, so I will stop there.